So today I'd like to tell you how to find a planet. But first let's take a step back and think about what that means. The nearest star is so far away that it would take a Concorde plane 2 million years to fly there, and most stars are further away than the nearest star. And because faraway things look smaller, at these distances the separation between a star and a planet orbiting it is absolutely tiny. It's about the same as the distance between my thumb and my little finger if I were standing 10 kilometers away. And because stars are much brighter than planets, the starlight completely dominates the image and makes it really hard to see the planet. So imagine that I jump on my bike, cycle 10 kilometers down the road, hold up my hand, light my thumb on fire and ask you to photograph my fingers. Pretty challenging, right? So how do I do it? Well, I start with a very large telescope. In fact, I use something called the Very Large Telescope, and that's an 8-meter mirror, so it's a single telescope mirror the size of this room and perfectly smooth and polished. And we need that because it's physically the most powerful zoom lens in the world. And with this telescope, we take a whole series of images, and we turn the telescope slightly between each one. And that's important because any noise in the images comes from tiny defects and scratches on the telescope surface. So as the telescope turns, the noise moves, but the planet in the sky stays in the same place. So that gives us a way to model the noise, subtract it all off, and reveal the planet signal. There's something else special about the Very Large Telescope, which is that there's an instrument on the back which has 20,000 prisms in it. As you know, when light passes through a prism, it's split into a rainbow of its component colours. So in my raw data, I get 20,000 rainbows, one for each point in the image. And some of that data is on the slide. Now, I've been working to take those rainbows, cut out each different colour, and turn them into a whole stack of images, one at each colour. And when we combine that with turning the telescope to subtract off the noise, we get cutouts like the 3 that I've displayed on the slide. Now, if we find a planet, we can look at it at 39 different colours. And by comparing its brightness at those colours, we can learn about the planet environment. We can find out how hot it is, and how strong the gravity is, and even whether there's water or methane in the planet atmosphere. One day, an astronomer comparing the amounts of water and methane in the atmosphere of a faraway planet will find a mismatch. And that will be a sign that there's alien life on that planet, which will be a pretty special moment. Now hopefully you spotted the planet in the cutout images on the screen. This is actually a well-known planet called Beta Pictoris b, which we were using to test our data reduction, make sure we were doing everything right. I haven't found any of my own planets yet, but I've found 79 maybe planets, and I'm working to determine if any of them are real. So hopefully one day soon, I'll find my own planet.